10.2, Graphing Exponential Functions. We are looking at the graphs today for exponential functions. We definitely are going to hit on domain and range again, and just on kind of some important features when we're looking at these new graphs. Before we go any further, let's remind ourselves that A, we know, is the initial amount. And we also know that at the A value, x is equal to 0. And B is our growth factor, or our decay factor, depending on what we're looking at. Okay, so let's go ahead and let's look at our graph. I'm going to start with the easy thing first, and that is what this little bubble here is pointing to, right? We're looking at this point right here. Okay, well, this point right here is on the y-axis, so we should know that this is our y-intercept. Okay, now what we might not know is that the y-intercept is our a value. This is our a value. Now I want you to think about that for a second. Isn't this point right here when x is 0? Yes, right? This is when x is 0. So this is our 0, comma, a, right? In this case, it would be 1, but that is also our y-intercept. So I'm going to add something here. And say, okay, well, that means it's our y-intercept. And that's going to help us later on when we write our equations. Now we got to talk about what this bubble is pointing to. I want you to write down a word, and this may be a new term for you, and the word is asymptote. It's a weird spelling, I know, right? This is pointing to what we call an asymptote. And so what I kind of thought I would do is I would demo what is going on here. The asymptote is a line where our graph gets really, really close to it, but doesn't actually touch it. So I'm going to draw the asymptote on this graph. Okay, it's this line right here. Now it totally looks like it's touching, but that's honestly just the limitation of my software when I made the graph. I can't show you how close it's getting. It's just getting close, 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 close. What I can show you is, let's go ahead and let's go to y equals. And I want to show you just a plain exponential graph here. All right, take a quick look at this graph. All right, it looks very similar to what we see graphed on the paper. What I'm going to do is I'm going to zoom in, and I'm going to go way, 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 way over here. Okay, and you can see that it looks like I'm touching 0, but look at my x value as I'm clicking. Do you see how my x values are getting negative and my y value is getting 0? But what if I zoom in? Okay, now can you tell that it's still saying 0 because it's so close, but wait a second, it wasn't 0 over here, right? If I zoom in again, okay, look, I didn't move my cursor. It's still saying 0, but can you see that it's not really touching? Let's do one more time, zoom in again. Look, it's not touching the x-axis. Now your calculator, the decimal's so small that your calculator says y equals 0. But clearly the graph, the blue line, is not touching the axis. The y value is not actually 0. It's just so close to 0 that we don't even bother writing the decimal. It'd be something like 0.000000001, right? It's so close to it, but it's not actually touching it. If we zoom out to the normal graph again, it looks like it's touching it, but I hope that now we know that it's not actually touching. It's just so close that our eye can't even tell how far apart they are, but know that it's not touching. That is the idea of an asymptote. Now we can have an asymptote in multiple different graphs, right? Like here in this graph, my asymptote would be right here, right? My asymptote would be right here. Both of those look like it would be where y is 0. Again, where y is 0, y is 0. But then look at these. Here's my asymptote. Right now it's approaching this line, whatever it is, looks like -2. Or here my asymptote is at +2, right? It's wherever it's leveling off. Exponential graphs always have an asymptote, right? So here the asymptote would be y equals 2. Here would be y equals, looks like -1. All right, you're always going to have an asymptote with an exponential graph. Okay. That was a long explanation. In this case, the equation for the asymptote is y equals 0. Again, this is the boundary line that our graph approaches, right? It gets super close to it. Our graph approaches, but never reaches. Okay. Every one of these exponentials has an asymptote. You guys, that was a long explanation. Let's just kind of see it and it'll make more sense. All right, domain and range, asymptotes, equations, y'all, we're really just looking at the graphs here today. Now, my domain, remember, domain is x values, right? Domain, we're talking about x values. So when I'm looking at this graph, I can tell that it's going up this way forever. It's also going left forever. Okay, well, it's going left forever, and it's going up, but also it's going up and right. It's getting further and further right every time. If my graph is going left forever and right forever, then my domain is all real numbers, right? From negative infinity to positive infinity, all real numbers. My range, however, what if I draw my asymptote on here again? Remember, these exponentials have an asymptote. It looks like it's touching 0, but it's not actually touching 0. This is my boundary line. The equation of this line, this asymptotic line, totic line, whatever you say, however you say that, okay, that equation is y equals 0. Again, never touches, so graph never touches this line. That's the definition of an asymptote. All right, so when I write my range, I hope we understand that all my y values are here or higher, right? But they never actually touch 0, so we have to say y is greater than 0, right? Greater than 0, basically above that x-axis. Now, if you put an or equal to symbol here, you're wrong. Remember, y is equal to 0. That's our asymptotic line. That's what it doesn't touch. So we cannot put an or equal to sign here. It's just y is greater than 0. Okay, my y-intercept is very easy to see, and that is the number 1. Whoops. Okay. Now, I'm going to go ahead and I'm going to write the equation for this thing. Let's remember really quickly that y equals ab to the x. Okay, we know that this is our initial amount, or it might be helpful to note this is my y-intercept. B is my growth or decay factor, right? We wrote this on the other side of this paper. Growth or decay factor. So let's go ahead and let's write the equation for this thing. Y equals, A is my initial amount, so that's 1. My growth factor, we don't know how to find it from a graph just yet, so I just give it to us. Our growth factor is 2, so that number goes in here. And then we have to the power of x, right? X is our exponent when we have exponential graphs. And I'm done. Let's look at the next one. We're going to go a little bit faster here. Again, x's are going left and right forever, right? This is going up and left forever, left and right forever, so all real numbers for my domain. My range, again, right, it never actually touches the x-axis, it's just as above it, so we say y is greater than 0. And why is it just greater than 0? Because there is an asymptote, right? It's never actually touching this line, this y equals 0 line. My y-intercept in this case is 5, so let's write our equation, and you can look here if you need to. My equation for this is y equals, A is 5, then my growth factor, you know what, that's a mistake. That should say decay. How do we know it's decay? Because it's between 0 and 1. So 0.5, right, that's my decay factor, to the power of x, and we're done. Okay, you might want to put a negative in this equation because you see it decreasing, but you need to remember that the reason it's decreasing is because this number is less than 1. Do not need a negative to make it exponential decay. That's the lesson today, guys. Remember, asymptote is an invisible boundary line, right? It's a boundary where your graph really gets close to it, approaches that line, but never actually touches it.